Yeah, and I'm here to talk about Chakra. In case it's not such a household name as V8, Chakra is the JavaScript engine in IE9 and IE10. And in April of this year at JSConf EU, Malte suggested that I come and talk about Chakra. I got really excited because even though we've been working on it for about 4 years, we really haven't spoken publicly very much about the internals. And then as the talk drew near, I realized that I have 30 minutes for it. Then I thought, oh crap, I'm going to have 30 minutes to tell you about what we've been up to in the last 4 years. And then it occurred to me that one of the best things I could do is shift over here to, let's see if you can see that. We'll switch over to my, this way, there we go. We'll fire off our command line JavaScript host, and I'll just run some JavaScript, and we'll spit out the machine code that we emit, and then I can kind of walk you through the details of it. And that'll probably fill about 30 minutes of our time, maybe a little bit more. So maybe it's not such a good idea. So instead of dazzling you with my compiler voodoo knowledge, I'll instead try to amaze you with my fancy animated slides. Let me take that one out of the way. All right, great. So Chakra, focus, there we go. Is that working now? There we go. Under the hood in 30 minutes or less. Let's see how much I can show you. So when we started the project 4 years ago, sometime late in 2008, we obviously wanted to rewrite the JavaScript engine to be faster. So we ripped out the old JavaScript engine from IE8. We added JIT compiler. Obviously, the main goal was to make things faster. But at the same time, we didn't want to sacrifice security, and we didn't want to sacrifice interoperability. As it turns out, adding a JIT to any process is a very juicy target for a potential attacker. We will take some performance hits in order to maintain security. We'll dive into this a little bit more. And then second, we wanted to be sure they were absolutely compliant with the ECMA script spec. So in the dark days of IE8 and before, you had to deal with all kinds of quirks and such. We wanted to be sure that that's not a problem in IE9 and beyond. So you want to be sure you write script once and it runs consistently on all the browsers. Yeah. And even our view of performance is somewhat more nuanced and balanced. We want to be sure that we are really good on page load because that's important, as well as on just the raw execution. And really what I want to tell you about is kind of the story of building Chakra, why it was built the way it was built, what's different about it than in some of the other engines, and then what is new in IE10 since we're just about ready to ship it publicly, officially. So we'll dive under the hood a little bit there. So let's start with security. Oh, by the way, I promised some assembly in my intro. There will be some of that. So that's a quick preview of what we're about to see. So security. When you add a JIT to the process, it becomes a very potentially juicy target for an attack. We want to be sure that our engine is not the source of exploits in the browser. If you think about what the JIT compiler does, it basically writes a bunch of data into memory and then points the CPU at that data and says, run that stuff. And if you're an attacker, that's almost exactly what you want to do. You want to be able to write some malicious code, and then you want the processor to run that for you. So if you can get a hold of the chunk of memory where the JIT compiler emitted some code, and then you can write your own stuff in there, you pretty much own the process. So you take a number of steps to make that as difficult as possible. For starters, the most important thing, the most important mitigation that we have, is we actually lock the pages that we write our code to. So we mark them as non-executable, non-writable, but executable, which means no one else can write to those pages any more data after we've generated the code. That minimizes the window that anyone can have to try to modify things after we've written them to that piece of code. And then we also make it difficult to figure out exactly where that code is emitted. First, we use some of the operating system mechanisms, the address space layout randomization. But then we also randomly lay out where the functions start. So we add some no-ops in the beginning. Sometimes there are no-ops, sometimes there are interrupt instructions. We actually emit some random no-ops within the body of a function, just randomly sprinkle them throughout, which again makes it that much more difficult to figure out where the code lives. And then it turns out that if you write JavaScript, you actually have control over some pieces of the data that we will write out. If you imagine when you have a constant, say value 12 somewhere, you say var x equals 12, that value has to be encoded somewhere. And then it turns out that it only takes 16 bits to encode an instruction in assembly on at least Intel's processors. So technically speaking, if you can have a constant that is 16 bits or more, you can put instructions directly in the code that we would emit. So to take that control away from you, we'll actually encode those 16-bit or more values by XORing them with some cookies. So that's what you see in here. And then on top of that, we do a couple of other things. We actually cap the amount of code that we will generate. That's to be sure you cannot fill the entire memory with random code and then jump somewhere there or write to a random location. And then when it actually comes to allocating pages, we also randomize those allocations. So all these things combined make it very difficult to own the code that we emit in any way. And the first part that I mentioned, the locking of the pages, is actually different between Chakra and any of the other engines. And does have some implications, like we ourselves are not able to modify the code after we wrote it out. So that's one of the cases where we will take some performance hit to get that security, and that's something that differentiates us from others. The other thing I mentioned was the compliance, spec compliance. ECMAScript is a well-written spec, but as every spec, it leaves some little nuances kind of up to interpretation. So we believe that it's important to have a suite of tests that can empirically verify that we all agree on what the spec says. So we worked with Google and with others to create the test 262, which now has 11,000 different tests that verify compliance with ECMAScript. And up until about 2 weeks ago, we were actually passing all of them. But then sometime 2 weeks ago, a few more were added to deal with UTF-8 encoding. And it turns out there's a bug in the underlying OS in some weird sorting algorithm that affects us. So we're now failing one test. But we're still actually doing quite well when it comes to the pass rate. And again, we're committed to making sure that we stay compliant with the spec. So if more tests are added that actually expose issues that we might have, we'll make sure we fix them. And the good news for you is, generally speaking, all the other browsers are also converging on a very high pass rate. So you can really count on your ECMAScript compliant script to run in all the browsers in the same way. OK, great. Most of the talk will be about performance, though. And I did say that we care about page load. Why do we care about page load? Well, even though the web is evolving and the apps are getting more fancy and more sophisticated, most of the people still experience the web as a bunch of pages that they navigate to. And their experience is primarily affected by how quickly those pages load. And since JavaScript execution is oftentimes on the critical path of that, we try to make sure that we get out of the way as quickly as we can. So that dictated that we kept an interpreter in Chakra. We have a compiler, but we retain the interpreter so we can start executing your code as fast as possible. So here's a quick little diagram of what we do with your code. When we see source code, we pass it through the parser. We produce an ASD. Then we feed it to a bytecode generator, which generates bytecode, which then we start interpreting as fast as we can. And please do appreciate my pulsating interpreter right there. But the main point here is we believe generating bytecode is faster than compiling to machine instructions. So in order to give you as fast startup as possible, we will get to the interpreter first, and we'll start executing there. But we do more. It turns out most of the sites bring in a bunch of JavaScript libraries, out of which only a small portion is ever executed. And even a smaller portion is executed at startup. So it's important that we don't spend all the time parsing all the code and generating the bytecode for all the stuff that is never used. So what we do instead is we defer parsing of anything that is not immediately executed. So we actually wait until you call a function before we do all the work that is required. There's a caveat there. Requirement of the spec is that we parse everything for syntax errors, but that's a relatively quick pass. So defer loading of your code is still a good idea because we will have to parse all of it, at least for syntax errors. But generally speaking, all the hard work is deferred until it's absolutely required. And we try to do even more. We try to preserve some of the information that we have between one page load and another. We'll actually keep track of the functions in your JavaScript that got executed to make sure that we parse those right away and we defer everything else. And then I'll tell you more about Windows 8 applications at the end. But for those written in JavaScript, we actually even cache the bytecode. So we don't have to parse or generate bytecode at all, which helps us greatly on startup for those. So page load is important, but of course we care about executing JavaScript as fast as possible too for the larger apps. So we start an interpreter, and as we interpret, we collect, there we go, profile information, basically data about what types of parameters, variables, properties we saw. It's kind of similar to what V8 does and what Firefox also does. And then we feed that information when the function is hot enough to start compiling into our JIT compiler, along with the bytecode for the given function. Now, what's different in Chakra is that we've bet heavily on concurrency. We believe there's a trend in hardware to having more and more cores, so you want to take advantage of them as much as possible. So in this case, our JIT compiler runs concurrently on a background thread. And if you have multiple cores, you can get the compilation while you're executing the code. So we can continue running your code in the interpreter, even as the JIT compiler produces machine code for a given function. And then when that machine code is ready, we will swap it back in, and then we'll continue executing just the machine code, not interpreted anymore. So that minimizes any pauses that might be introduced on the UI thread by compilation. Everything is done on the background thread. And then another component of the system, the garbage collector, is also designed to be run concurrently as much as possible. Most of the marking and the sweeping that we do, we have a mark and sweep collector, is actually done concurrently as well. There are some portions that we have to do on the UI thread. I won't get into great detail of that. But for the most part, we do the bulk of the work concurrently. So if you have 3 cores, and if you need to compile and garbage collect and run your code concurrently, we can do all that stuff as long as you have enough cores. And we believe we can actually expand that relatively easily to parallelize over more cores if those become available. So that's the key aspect of our architecture that is different from other browsers. And then the rest of the talk I'll spend talking about the changes we've made in IE10, particularly in our JIT compiler, because we've changed it quite dramatically. So you may or may not know that in IE9, we were able to generate machine code only for x86. If you ran a 64-bit version of IE9, you were actually running in the interpreter only. In IE10, we added machine code for x64 and for ARM as well. So in all these cases, we have full JIT compilers now. And then we changed the general philosophy of our JIT code that we emit. I'll talk about that in some detail, but we kind of adopted a similar model that you see in other browsers today of generating optimistic code, and then if things go wrong, then we'll just bail out and we re-JIT if we need to. And that gives us a number of other benefits. We can generate faster math, both floating point and integer. We can do function inlining, and we actually have a number of other optimizations that are just strictly from the compiler land. And we also added support for typed arrays. That's not really a compiler optimization, but it gives you, if you really want access to native data, that is critical. All right, so the optimistic profile-based JIT. What is that beast? Now, if you were hanging out in the bubble room this morning, you probably have seen much of that explained, but for those who weren't there, I'll cover some of the basics. So in IE9, the code that we would emit looks kind of like this graphically. We basically try to handle all the nooks and crannies of the JavaScript semantics. Say if you have A plus B, maybe 2 numbers that you have to add, but maybe it's 2 strings that you have to concatenate or what have you. We were trying to handle all these cases, which meant for everything other than integers, we'd have to call into the runtime to do the operation, get back the result, and then try to continue, which oftentimes meant that we had to call back into the runtime and back and forth. So for integer operations, we were generally pretty good, but for certain other things, we were not. In IE10, we're doing things differently. So we will collect the profile that I mentioned before. So now we know that we primarily operate, say, on floating point numbers. So we'll generate the code that is specialized for those, which typically results in a much shorter and more compact and more efficient code. But then we have to check that the conditions that we expect are still true. So if now we pass us a bunch of strings, we have to do something else. So that's the little diamond on top. We check the conditions. And if they turn out to be false, we have to bail out. So in our case, bailing out means transferring the state of execution over to the interpreter and then continuing that function in the interpreter. When we call the function again, we will re-enter the JIT code. If the conditions are still not met, we will bail out again. If that happens sufficiently frequently, we will decide that it's time to re-JIT that code with a different set of conditions. Maybe it's a more generic code again that is a little slower, but if that's the data you gave us, that's what we have to work with. So generally speaking, our code adapts over time to the data that you pass us. Great. And I mentioned that gives us a chance to generate more efficient code. But first, a little bit of a background, why that even matters. You probably are well familiar that in JavaScript, variables are dynamically typed. So at any given point, say A in this case could be a number first, then a floating point number, then a string, then an object, then even a piece of date. And we have to deal with all those different values. So typically they were encoded on the heap with some form of a type tag and then the value to tell us how to deal with those types of values. And they have to be allocated on the heap, and then the garbage collector, when they're no longer used, has to collect them all, which has a high overhead, of course, when it comes to memory. And then this also means that the basic operations are quite inefficient. So if you just take this simple a plus b plus c, you kind of break it down into individual operations. You have to add a and b, and then add the result to c, and then return that. It turns out that it's this lengthy sequence of things that you have to do. So you have to get a type of A, type of B, then the value of A and value of B. Then based on the types, we have to decide what to do. Maybe it's adding two numbers, maybe it's concatenating strings. Then finally, we have to execute that operation, get the result back, stick it back on the heap, and only then we can return it. So that's very inefficient. In IE9, we employ the same trick that most of the modern engines now do, and that's kind of a common thing in dynamically typed languages. We use number tagging. If you're not familiar with it, the idea is generally pointers are aligned to a certain boundary, so the least significant bits, typically 3 or 4, are always 0. So we can stick a 1 in one of those bits and then use the rest of the bits to actually store the value of the integer. So like in this case, the number 3 can be encoded directly in the register or on the stack. That helps because we don't have to allocate it on a heap and grab it from a heap every single time. So in IE9, we were using that. In IE10, on the 64-bit platform, we have more bits available, so we can stick floating point numbers and large integers also directly into registers on a stack. So that helps with math operations. There's still a long sequence of steps, but each of those steps is a whole lot cheaper. So when it comes to grabbing the type, we just have to check for that one bit. We don't have to go to the heap. To get the value, we just have to remove the bit. That's also cheaper. Then we know what operation to do. We just add two numbers. And at the end, we just have to tag the number instead of sticking it back on the heap. Great. So that was better than in IE8. But in IE10, we can do much better than that. Because now we don't have to worry about all the other conditions that we might want to handle. So that's just an example of a set of operations that we will do from the SunSpider benchmark. This little loop right there basically translates into that assembly that you see on the right. And if you're well versed in assembly, you can get an idea that that is just about as tight as it can be. That's something that a C++ compiler wouldn't be particularly ashamed of generating for the same kind of code. So it's quite efficient. With the one little exception over there, we have to check for the overflow, which is just required by the semantics of the JavaScript operations. And if overflow happens, you will notice we'll actually bail out of this code and we'll try to reach it. So that makes integer math much faster. For floating point math, this is even more important because previously you always have to box the floating point numbers back and forth. Another example from SunSpider, and again, if you look at the instructions on the right, it's basically just floating point operations on registers. So it's quite efficient. A couple exceptions there. We actually take a register spill, this move SD that is marked in red. Our linear scan register allocator has some limitations. In this case, it chose to spill this register. And then there's also the overflow check. But again, generally speaking, for local variables, for parameters, we can generate very tight and very efficient floating point and integer math. There are some limitations to it. When you start sticking those values into properties or extracting them from properties, we still have to box them or tag them. And it turns out that you do actually do a lot of operations on properties. So property access is also important. And we did a lot to make it faster in IE9. We did even more in IE10. I'll cover some of that in the next few slides. So generally speaking, again, as a background, which may be obvious, JavaScript objects, just bags of properties. So traditionally, you never knew if you wanted to grab property X, you never knew where to find the value of that property. You always had to do a dictionary lookup, get the value, and then the same thing next time around. Inline caches are typically used to help that. What they really are just a way to remember some information. So if you remember the object that you saw before and know where to find property X, next time you can do it faster. All right, so in IE9, we added inline caches. And for the inline caches, we had to keep track of shapes of the objects or internal classes, as they're called in V8. and we typically call them internal types. So here's an example of a constructor that creates two different objects and just gives them X and Y properties. And shapes are basically sequences of properties that are added to an object. So we follow the evolution of an object, and then we associate a certain shape with that object. So here, the shape would be XY, and the bubble indicates that it's derived from a certain prototype. If then you create the second object, B2, which follows the exact same code path, it'll have the same type or shape, and then subsequent accesses to properties of those objects will be monomorphic, meaning the objects will have the same shape. And we can do quite well in IE9 for those types of objects. Here's just a quick example. If you now call this reset method in a loop, which then tries to set X and Y to 0, we have an inline cache associated right here with that instruction. And the inline cache remembers the type and remembers the slot at which we found property X last time. It starts zeroed out, there's nothing there. And this is roughly the code that we would emit to access that property. You don't have to understand all of it. The key thing here is we check the type or the shape of the object against the shape that we remember in the inline cache. Right now, they don't match because the cache is not initialized, so we have to do a slow lookup. But after we're done, we store that information in the inline cache. And so next time around, when you go through that loop and get to this type check, it succeeds. And so if it succeeds, we have a fast way of getting or setting the value of that property. We just emit those three instructions. So that works really well if the shapes match. But in JavaScript, you can throw additional properties into objects afterwards. And in this case, if B2 got a property C, now it has a different shape. So we have two different objects with different shapes. And so accesses become polymorphic. And in IE9, there are some limitations to how fast we can be with polymorphic properties because we only remember one type at a time. So here's the same example with those two modified objects. And we start off the same way. We populate the cache. But then on a second iteration of the loop, when it comes to this check, we remember XY. What we have now is XYZ. So the types don't match. And we have to go down the slow path. So basically, in the worst possible case, if you were just flip-flopping between two different types, we would always go down the slow path, and our inline caches weren't particularly helpful. It turned out that for the most part, the accesses aren't exactly alternating like that. So most of the time, you're still hitting the cache, but there's some performance overhead of polymorphic properties. So in IE10, we actually added true polymorphic caches that can keep track of virtually unlimited number of types. So our polymorphic property access is much better. And then we took advantage of the optimistic code generation to get better property access using object type specialization. I'll explain that. And then we generally streamlined our object layout to make them thinner and requiring fewer allocations. And then some of the compiler optimizations added also apply to those. And so here's an example. On the left-hand side, it would be the code that we would generate in IE9 to add the values of those three properties. And on the right-hand side is what we do in IE10. So in IE9, you see that we execute the same sequence of operations for every one of those property loads. And we check the type of O every single time, even though it's the same object O. So it seems redundant. It turns out it wasn't trivial to eliminate. But in IE10, we did get smarter. We just emit this check once. And then subsequent property loads, we just know exactly where to find X, Y, and Z once we know the shape of O. And you notice those bailout instructions there on the right. Those basically mean that if the object's shape does not match, we have to jump out to the interpreter, and we have to deal with it there. And we will recompile the function later. So this is great. That actually is more efficient. Where you get the biggest bang for the buck is when that type of instruction is executed in a loop. With the loop invariant code motion, we can detect that the object O is not changing, and we can hoist all these expensive checks outside of the loop. We run them once, and then in the loop, that executes multiple times, we avoid the overhead. In this trivial example, it turns out that X, Y, and Z also don't change, so we hoist the loads of those. And since they don't change, the plus operations are also redundant, and they can be moved out of the loop. So in this trivial example, the loop itself becomes quite trivial. But then if you were to insert a function call into that loop, we would have a problem. Because it turns out in JavaScript, function calls can change half of the world. So the function calculate, for all we know, could be changing the shape of O. Maybe it removed property X or something. And so now we have to execute all these checks and all these loads on every iteration of the loop. So function calls tend to kill most of the optimizations that any of the engines can do. And that's why function inlining is such a critical piece of every JavaScript engine today. So if we can inline calculate, we can see inside, and we can prove that O still doesn't change and XYZ still doesn't change. So all these things can be still hoisted outside of the loop. So not only do we eliminate the overhead of the function call, but we get to retain some of the other optimizations that we did before. So inlining in IE10 is also a great benefit. And so, yeah, so better math, better property access, function inlining, those are the critical pieces that we added in IE10. And that kind of covers the basics of the JIT compiler. And I have about 5 minutes left. I only want to mention a couple of additional things. I alluded to this already. You may or may not know that in Windows 8, we actually took a big bet on JavaScript and HTML. So you can build native applications in Windows 8 using web technologies. They're not run in any kind of a web controller or anything like that. They're actually native apps that have access to all the native APIs. And in fact, several of the apps that we ship in box with Windows 8 are written in JavaScript and HTML. So if you ever wanted to stretch your muscle, flex your JavaScript muscles on a different platform, you're definitely encouraged to try to grab the Windows 8 and then try to play with it. We think it's an interesting opportunity, and it's definitely, we believe that it's where the future is, and we want to support the platform, the web platform, as a way of developing apps for Windows 8. And then my last cheesy slide for the day. Are we done? Of course we're not. There's a bunch of other things that we'd like to do. There are some things that are not as efficient as they should be, but there's also a bunch of trends that we kind of follow that we want to make sure Chakra is a great engine for. So of course, as ES5 gets more adoption, there are certain things we like to optimize. As ECMAScript 6 is evolving, we also want to be sure that we first comply with the spec, second, that the implementation is fast. HTML5 games, certainly an important target for us. Windows 8 apps, of course, we want to make sure that they run very fast. And then other things, web workers are an interesting trend, for instance. Maybe more concurrent compilation, maybe more concurrent garbage collection as in order to handle concurrency in advanced apps, and so on and so forth. The bottom line is we want to be sure that Chakra is a great platform for building the kind of apps that you want to build today and tomorrow. And with that, I think we have about 3 minutes left, so I'm happy to take questions. You can also grab me by email or Twitter.
Want to kick it off?
Thanks for that. I had a quick question. You said that you just-in-time compile in 64-bit, but I was under the impression that data execution protection was mandatory for 64-bit applications, so which would make the memory not executable. How do you get around that?
No, there is an API that a process can call to make a piece of executable or data executable, and we call that API. But what we make sure is that the window of time that you have to potentially override the code that we emitted before it's locked up is minimal. It's just really the time between we copy the buffer into the right page and we lock it.
So my main question is, can you actually see the generated code on a normal Chakra, not on some custom build?
No, you can't. That's an internal tool that basically hosts Chakra in a statically, well, if you're able to build a checked build of Chakra, then yes, all the switches for dumping the output are there, but that's not what we ship.
I have a question about the inline caches.
Yes.
So since you can't actually write into the memory once it's been, the code has already been generated, where do you actually keep the inline
Yes, that's
cache?
an excellent question. I forgot to mention that specifically. So inline caches are implemented differently on different engines. In some cases, an inline cache is actually a snippet of code with directly hard-coded values. In our case, it cannot be, because we need to be able to update the cache. So for us, a cache is just a piece of data that our code references. So we have we hard code the location of the inline cache in the assembly that we emit, but then the cache itself is just data and is not protected, so we can overwrite it. Does that make sense? Okay. All right.
So you mentioned bytecode caching for Windows 8 apps. So you compile the bytecode and put that in the store, and we download that. Does that work for, or am I correct in how that works? And why don't you do that for caching JavaScript in IE10
Right.
itself?
So it's actually slightly different than that. We generate bytecode on the target machine. When you install the app, we schedule the bytecode generation sort of in the background, and whenever that is available, we will start using the bytecode. Until then, we can still run from source code. There is no limitation there. So the bytecode is not in the store, strictly speaking. It's on the machine. We did contemplate putting it in the browser, and it's still very much a question that we're considering. It's a little harder in a sense that you don't have a moment when the app is installed in the box, and certainly JavaScript can be, the JavaScript that you load can be changing more frequently than the app that is installed in the box. But there's nothing technically making it impossible, and we certainly are contemplating that as well. Yes?
Will Windows Phone 8 be running Chakra too?
Well, Windows Phone 8, yes, we'll get IE10, yes.
Okay, that didn't answer the question.
What do you mean by Chakra 2? You mean
will it run the same JavaScript engine?
Yeah.
Okay.
Sorry.
Any other questions? All right, looks like that's it. Thank you very much,
Thanks
Andrew.
very much.